Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to go past Mars, past Jupiter, past Saturn. We're going to go past Pluto. We're going to go to the nearby stars. That's right. We're going to talk about starships because that's what we physicists are talking about. Engineers, of course, talk about going to Mars. But we physicists are dreamers. And we want to know, well, is it physically possible to send people to Alpha Centauri, the closest star to the planet Earth, only a hop, skip, and a jump of 24 trillion miles? A Saturn rocket? Well, a Saturn rocket would take 70,000 years to reach Alpha Centauri. So obviously, we need to go beyond chemical rockets. We have to go to atomic rockets, antimatter rockets, warp drive, you name it. We physicists have looked at the physics behind some of these speculative designs. And if you saw the movie Passengers, it starts off on a starship. The distances are so great that you have to go under suspended animation to reach a new home orbiting another star in the universe. And already, we scientists have identified 3,600 planets orbiting other star systems in the Milky Way galaxy. And so we know they're out there. And in the movie Passengers, well, A-list Hollywood actors go to the nearest star, go to a star with an Earth-like planet going around it. And if you saw Matthew McConaughey in the movie Interstellar, we go even past that. We go to the other side of the galaxy, going through a wormhole. And so in this hour, we're going to talk about wormholes. We're going to talk about different kinds of rocket designs. And my colleague, Stephen Hawking, has another idea that may take us to the stars in maybe a quarter of a century, 25 years. And that is, why not send tiny computer chips? Put a sail, a parachute, around each computer chip, blast the parachute with a laser beam, and because it's so small and compact, you could send it to a fraction of the speed of light within just a few minutes. Think about that. Thousands of these little tiny chips being blasted by laser beams to the nearest star, and in 20 years, they would reach Alpha Centauri. And if you've been following the newspapers, you know that there is a planet orbiting one of the stars in the Alpha Centauri system. It weighs about 30% more than the planet Earth. It is Earth-like. Think about that. One day, we may be able to make contact with an Earth-like planet orbiting around the nearest star in the heavens. This is a dream from science fiction taking place not in the 23rd century, taking place maybe in 25 years or so. Well, let's talk about the science behind all these things. With us today is Dr. James Benford. He and his brother Gregory Benford are physicists and science fiction writers. That's right, they write award-winning science fiction tales. And they're also authors of an anthology called Starships Century, where they invite the leaders in this field, both in fiction and in fact, to write articles about what it would take to journey to the nearby stars. And again, this is something that we cannot do. We won't be able to do for a few more decades. But hey, we're thinking about it now. So we're sort of like in the 1950s when people were thinking about going to the moon, but the whole idea was so preposterous and outlandish. Well, we went to the moon. Now our sights are set on the nearest star in the heavens. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Dr. James Benford, and he and his twin brother are experts in physics and starship propulsion systems and science fiction. They're the co-authors of a book that I highly recommend called Starships Century. It's an anthology consisting of articles written by physicists, my friends in fact, as well as science fiction writers. So if you were interested in exploring the universe, the book to get is Starship Century. Once again, our special guest today is Dr. James Benford, twin brother of Gregory Benford. And they hail from Alabama. And he studied physics at the University of Oklahoma. In 1969, he got his Ph.D. in physics from the University of California at San Diego. He's worked for 26 years at Physics International. In 1996, he founded Microwave Sciences, and he's an expert on high-powered microwave systems. And in this hour, we'll talk about science fiction and science fact and how to get to the stars. So, Dr. Benford, glad you could be on Science Fantastic.
I'm happy to be here.
Okay, well, let's just jump right in. You are a physicist. However, most physicists, well, their eyes kind of like roll into the heavens when you talk about starships and Star Trek and science fiction and stuff like that. So let me ask you the first question. As a youth, when you were a kid, how did you first get interested in science?
I got interested in science through science fiction. I started reading Robert Heinlein juvenile novels, the first of which was Space Cadet, and eventually I read all of them. They're a wonderful set of encouraging, positive books. And that got me so interested in space that I realized if I really wanted to participate in that, which I saw as the thing that would happen in the near future, then I had to learn science, I had to study mathematics, and I had to get serious in life. That was at the age of about 10.
Okay, and then what steered you in the direction of physics as well as science fiction?
Well, physics is the hardest thing in many ways, and I figured if I could do the hardest thing, then I can do the others as well.
Okay, so I guess you figured that if you had a good physics background, that would allow you to then explore the realm of science fiction, right?
And the other sciences. I mean, physics is a harsh discipline in a way. You have to change the way you think, and once you've done that, you can think about anything practically.
Okay. Now, I've gone through your book, Starship Century, which I think is a great book. It's a great primer for those people who are serious about looking into the possibility of one day going to the stars. So what was the genesis of that book that you and your twin brother decided to put together?
Well, I participated in organizing capacity of a meeting in 2011 called 100-Year Starship Conference in Florida. And it made me realize that this is a coming thing, that starships were finally beginning to be taken seriously. And so I suggested to my brother that we produce an anthology of both science and science fiction about Starship with the many people we know in the field and put together something that would advocate that we take this matter seriously and to encourage people to get interested enough, to get educated enough, and to make something happen in this direction.
Okay. Now, let's talk about what it would take to build a starship. Most people, of course, have heard about the plans to go to Mars, and we've sent space probes out to Pluto. But what would it take? If I had a Saturn rocket, how long would it take, roughly, for a Saturn rocket to reach the nearest star, Alpha Centauri?
Rough order of magnitude is about 100,000 years. About as long as the human beings have been a species.
So, in other words, we can rule out chemical rockets, right? That's a no-go.
Forget about it.
Okay, so no Saturn rocket is going to take us beyond Pluto into deep interstellar space and onto Alpha Centauri, which is only, 24 trillion miles from the planet Earth.
Yeah, right next door.
Okay, now, a few years ago, Stephen Hawking, my colleague, had a press conference where he advocated a new way of going to the stars, not with the Starship Enterprise, a gigantic, sleek starship that has hundreds of crew members, but having postage stamp chips that are propelled by laser beams that would take maybe 20 years to go to Alpha Centauri. So could you explain what's the motivation of sending postage stamp chips to the nearest stars propelled by laser beams?
For that to be a payload means a great deal of miniaturization compared to today's probes. But the downsizing of electronics and various things like cameras is proceeding at a tremendous pace. And it is credible to make a postage stamp 1 gram payload credible. In fact, I have a few prototypes here in my office. They were fabricated largely by Cornell and Harvard. So we think we can get a limited amount of diagnostics onto such a probe, such a payload, but then you can send many of them. The idea of using a laser beam to drive them is that you can launch one today and another one tomorrow and keep on going, so they don't have to all get there. You can take risks with them, and once they get there, they can report on specific things back to Earth. You don't put everything on one platform, so to speak, such as our Voyager probes or our New Horizon probe, where all the diagnostics are in one probe, and it's the major investment. So this is a kind of a fire and forget system in the sense that you launch it, and then it's on its trajectory with a little bit of maneuvering on the way, and does a flyby. And so it doesn't have to decelerate at the other end. The project is called Starshot, and it's been underway. This is its second year, and I should say that I'm one of the principal participants in Starshot. We didn't mention that what the laser beam propels is actually a sail with the payload on it. By a sail, I mean a fairly large area, some meters in diameter, which is diaphanous, that is extremely lightweight, on the order of a gram, and is accelerated at tremendous rate to very high velocities in just a matter of minutes. The numbers fit together, and it's a very challenging project, but the key elements are the sail, the payload, and the laser, and my responsibility is the sail.
Okay, well, when you start to look at the details, you realize that the bank of laser beams has to generate 800 gigawatts of power. That's the power of, 800 nuclear power plants. That's a lot of power and a lot of money, right? What are your thoughts?
It's the major driver in the cost of the system is the laser and its radiating aperture. I think you're off a bit on the number there. It's on the order of about between 10 and 100 gigawatts power. Now, it's still a very large number.
Right.
And that's hard to do. You can't do it with a single laser. You will need millions of lasers. And that is, I think, the very basic challenge to the program is how to coordinate that many small laser devices, which will all be fabricated by essentially chip techniques and microelectronics. They won't be large structures, but small ones, and replicated in vast numbers. But the laser is a really big challenge for the project.
Okay, now the laser sales, of course, are going to cost a lot of money, and we need banks of these lasers. So we have billionaires that are backing this program, right? I mean, $100 million has already been pledged to this project. It'll cost $10 billion to make it into fruition. And I understand that Mark Zuckerberg, the founder of Facebook, is behind this project as well. So you have some billionaires out there, right?
That's true. There are at least two billionaires associated with the project, Yuri Milner and Mark Zuckerberg.
Okay, and what about NASA funding? Is NASA going to get behind this thing too? Because $10 billion is a lot of money.
NASA is not directly involved now, although some people who work with NASA have attended some meetings, and NASA has just very recently started a small $500,000 project to think about where to go with Interstellar. And I think that probably is because of the publicity having to do with Starshot. Some people in Congress are saying, hey, why aren't we doing something if this is a good idea?
Okay. Now, also, when you want to aim something all the way out to Alpha Centauri, the nearest star, 24 trillion miles away, that's a lot of aiming technology, right? Do we have the technology to aim something so precisely that it would travel 4 light years to the nearest star?
First of all, it would require the very state-of-the-art, the very best we've ever done in pointing accuracy on the order of 10 nanoradians. Secondly, you're going to have some ability to tack this sail, so to speak, to maneuver it so that it goes where it's supposed to do. You've always got to have the capability of having, so to speak, a mid-course correction to the trajectory. And let's face it, sometimes you're going to miss. But on the way, you'll get data about the interstellar medium and cosmic dust and things like that. But pointing and tracking is a really big challenge to the project. In fact, we're going to go through this. If we go through this completely, I can list for you 5 or 10 major challenges for the project. It's a very audacious and ambitious project.
Now, when a laser beam goes through the air, you lose about 90% of the energy. So some people are saying that because this project will come to fruition in a few decades, why not put it on the moon? Of course, that's very expensive. But if you have all these lasers on the moon, you would have 10 times the power without having the atmosphere absorb so much energy. But what are your thoughts? Is that for the next project?
What we plan to do is to locate the laser at very high altitude, probably the Atacama Desert in Chile, where most of the atmosphere, certainly most of the water in the atmosphere, which is an absorbing medium, that is far below you. It's the driest place on the planet, and therefore the losses are kept down to a much lower level. And indeed, the laser is the dominant cost in the system, and so once you've built it, you use it many times, and you putting it in space would make it cost orders of magnitude more, and therefore make it unaffordable.
Okay, and I think the appealing thing about this idea is the phrase off-the-shelf technology. I mean, we're not talking about inventing new laws of physics here, right? We're talking about simply throwing money at systems that have already been shown to work, right?
That's exactly right. There are really 3 kinds of issues in any major project of this kind. The first is the science, that is the physics. In this case, the physics is known. We're not talking about anything new. The next challenge is engineering, and that's where the bulk of the challenge lies. And we have many issues to deal with in engineering. And the final decider is cost. How much can we afford to spend? And in fact, if you take the engineering challenges plus the challenges of cost control and getting costs down by mass production, those are sufficient to make it a very challenging project, but we require no new physics here.
Okay, and you were involved with the 100-year Starship idea that you mentioned earlier.
Yes.
However, with off-the-shelf technology, we might be able to have this system up and running perhaps in a few decades, right? We don't have to wait 100 years, maybe 2 or 3 decades. So what are your thoughts?
Yeah, precisely. I think we are likely to be able to deal with these engineering problems within a timescale of a decade. And at that time, to be building a demonstrator which will show the basic features of the system working together. And then having success in that, we will move on to the big system, the full system, which will take 10 to 20 years to get into place fully. And therefore, I expect that we will be launching probes toward the stars within somewhere about something on the order of a quarter of a century from now. And therefore, probes will reach the stars in this century.
And when Mother Nature wants to send something from A to B like seeds, she sends thousands of seeds, hoping that a few of them germinate. So in this situation here, because we're talking about small little chips being sent to near light velocity, you could send thousands of them, right?
Yes, that's why we want to launch frequently. And many that's what you do. Once you build the launcher, you've paid the price, so you may as well send as many as you can.
Well, let's take a short commercial break, and after the break, we're going to continue a discussion of starships with Dr. James Benford. He and his twin brother are co-authors of a delightful book called Starships Century, Toward the Grandest Horizon. Welcome back to Science Fantastic with Professor Michio Kaku. We're very delighted to have with us today Dr. James Benford, a physicist who also dabbles in science fiction. And he and his twin brother are authors of a book, Starship Century, because that's what we're talking about today. What are the chances that we might be able to not just go to Pluto? I mean, we're talking about going way past Pluto. We're talking about going to the nearest star. Alpha Centauri is over 4 light years from the planet Earth. And recently, astronomers have found an Earth-like planet going around one of the stars in the Centauri system. It's called Proxima Centauri b. It is Earth-like, just a little bit bigger than the planet Earth. And who knows? Maybe there are people on Proxima Centauri b who are wondering whether or not there's any life on this planet. So the possibility of a starship within, let's say, 25 years or so is a real possibility. So, Dr. Benford, let's continue a discussion about this laser system. Isn't it true that this is part of a larger set of starships? The laser, the sails, the photon sails that can reach a fraction of the speed of light. So not just laser beams, but some people have thought about maybe the sun as a source of energy, but probably not enough to go to the stars. But isn't it true that there's a whole variety of these sail systems?
Yes, some of them are quite large and go more slowly, have bigger payloads. And in fact, we should look at the entire class of beam-driven sails to think about how we could use this technology to get around the solar system much faster than we do now. Because in interplanetary travel, we have reached the limits of chemical rockets quite a long time ago. And what we need now is both faster ships, but also ships that have a much bigger payloads. And in the first category of faster ships, the beam-driven sails will top anything. They can be driven to very high velocities. In the question of heavier payloads, we probably need to go to nuclear rockets, either fission rockets or fusion rockets. And only the former, the fission rocket, has been demonstrated in a very practical way. Fusion is still a long way off.
Okay, well, let's talk about those nuclear rockets. Several decades ago, physicists like Ted Taylor proposed the Project Orion using small mini nuclear bombs. You eject them from the rear of your starship. You essentially ride on the shock wave created by a nuclear detonation underneath your starship. And by golly, it could work, right? I mean, at least on paper, it is possible to create a starship using mini hydrogen bombs dropped out the rear end, right?
It's credible. In fact, a demonstration was done using chemical explosives.
Way back in the 60s in San Diego, propelling an object up to some altitude, not very high, but showed that in principle this would work. Well, in practice, it was using just high explosives. Now, with the nuclear explosives, it's a pretty inefficient use of nuclear explosives, but I can't think of a better use. And it's not probably the way I would go. I think that using an atomic pile which heats hydrogen into an exhaust nozzle is a much more efficient way to use nuclear energy.
And by the way, Ted Taylor, the man who was behind Project Orion, was actually an acquaintance of mine, and I asked him why he finally gave up on the idea of using pulsed hydrogen bombs to propel a starship. And he said, well, basically 2 reasons. First, there was a limited test ban treaty, so you couldn't test these things. And second of all, he was worried that nuclear weapons would get so tiny and so versatile and so hidden that terrorists could get a hold of these things and cause tremendous damage. And so he decided not to work on these mini nuclear weapons, these micro nuclear weapons, because of the possibility of proliferation. Well, let's now move away from fission, that is the power of uranium, to the power of fusion. And fusion, of course, is what makes the sun shine. It's what makes the stars shine. And, well, we have to take a short commercial break. But after the break, I'll ask you about fusion engines and then antimatter engines. We don't have them yet. But one day, perhaps in the 23rd century, when Star Trek is in the 23rd century, we'll have antimatter rockets as well. Well, let's take a short commercial break. In the next segment, we're going to go to the stars, perhaps riding on antimatter. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Dr. James Benford. He and his twin brother are authors of the book Starships Century, and we're talking about starships. We led off by talking about laser sails, that is, riding on the power of a laser beam to propel a small chip out to the nearby stars, maybe within 25 years. There's also an older idea using nuclear weapons and riding on the shock wave of nuclear weapons to propel a starship. Then there are fusion nuclear power plants that use the power of hydrogen, and then there's antimatter rockets. Well, say a few things, Dr. Benford. Tell us a few things about antimatter rockets and why we're not going to have them anytime soon. But at least on paper, an antimatter rocket would take us near the speed of light, right?
True, on paper. There's a complexity to it. Basically, the rocket works by the annihilation of an antiproton and a proton. But it does not produce gamma rays immediately. Okay, it doesn't result in gammas flying out behind the rocket. Instead, the annihilation produces several short-lived elementary particles called pi mesons or pions, and they produce about 3 per annihilation, and they can then be captured by a magnetic field of a magnetic nozzle. That is, their paths can be bent into curves by a strong magnetic field, and they have to be contained and controlled and directed by these fields as along the exhaust. But that means that the charged pions can heat up a liquid, for example, like a liquid hydrogen, so that the hydrogen receives energy and you have a hydrogen exhaust. That doesn't give you such a high speed, though, because it's just heated hydrogen. And therefore, the magnetic nozzle has to be long enough for that conversion to take place, which is, if you want to get all the particles and all the energy out, you've got to have magnetic nozzle that's on the order of a mile in length. Now, if you just want to get the first generation of pions, you can cut it down to perhaps on the order of 100 meters. But it's still a big magnetic structure, and therefore the scale of such rockets is going to be quite large.
In fact, all these rockets that we're talking about, the nuclear rocket, the fission, the fusion, and the antimatter rocket, they are huge, right? They're not simple things. They're gigantic objects in outer space.
First of all, I should make clear that fission rockets, which use the fissioning of plutonium or uranium, are not going to give us starships because the exhaust velocity is just not high enough. But they are, on the other hand, not much larger than Saturn V's. And they are a good way to get a lot of payload around the solar system. In fact, we developed them completely, and so did the Soviets, back in the 60s and 70s, to the point where they were really ready for Mars missions, but then got mothballed because of anti-nuclear sentiment and various other political forces in the early 70s. But they're still there, in storage out in Nevada, that we could take that technology up again, since it was really quite well developed back almost 50 years ago. That's the fission rocket. Now, the fusion rockets will certainly be very large. There's been a very recent study called the Icarus Project, which has looked at how to build a fusion reactor that it can propel a starship, and how to do that with 21st century technologies. They turn out to be very, very large, on the order of the largest ocean vessels. I mean, think about it, on the order of a kilometer in size, and therefore massive and expensive, and with an awful lot of fuel, because the rocket equation dictates that in order to get to high speeds, you've got to have tremendous amounts of fuel, and that most of the volume goes to fuel storage, and most of the mass goes to the fuel. And then, of course, you can put some serious payloads out to the stars on the timescales of several decades. So fusion rockets are a possibility if we can get fusion to work. Now, I spent about 20 years of my life working on fusion, and I know it's a very hard problem. And until we really get that problem solved to the extent that we can use it in rockets, those concepts are not going to be realized.
Okay, well, let's take another short commercial break. The subject for today is watching the movies. You know that we're way past Pluto. If you saw the movie Passengers, yes, we're going to another star in the universe in that movie, starting some A-list Hollywood stars. And if you saw the movie Interstellar with Matthew McConaughey, you know that perhaps one day we'll be going through a wormhole and zipping across to the other side of the galaxy. Well, let's get back down to Earth now. With us today is Dr. James Benford. He and his twin brother, both physicists and both science fiction buffs, have co-authored a book, Starship Century, about what it would take to go to the nearest stars. So we talked about laser sails riding on a laser beam. We talked about fission rockets riding on a hail of nuclear weapons. We talked about fusion rockets, antimatter rockets, and now let's talk about ramjet engines. When you take a look at a jet does not have that much oxidizer because it scoops up air from the outside, saving space on the jet. Well, why not have a rocket ship that scoops up hydrogen in interstellar space, then fuses the hydrogen to create fuel? Then you're simply getting hydrogen for free. There's a lot of free hydrogen out there. Why not scoop it up, fuse it inside your chamber, and use that for exhaust? Well, tell us about the pros and cons of ramjet fusion engines that don't need any external or any fuel source whatsoever.
Well, there certainly are pros and cons. The great thing about the Bussard ramjet, and Bob Bussard was a friend of mine for many decades, and I did work with him, is that you don't have to bring your fuel with you. You collect it in the interstellar medium. Now, Bob assumed that the density of interstellar matter would be that of globular clusters. Turns out that we're in a rather vacant area of the galaxy where the density is far smaller, and therefore interstellar ramjets don't make much sense for humanity, but they certainly would make more sense if one were in a much more denser region, such as toward the center of the galaxy or globular clusters. But given that, if you have a very big web of magnetic field that will capture these hydrogen atoms as they come in, ionize them, and push them down the throat of a fusion engine, then you have a way of accelerating and accelerating and accelerating, and you don't run out of fuel, so you just get faster and faster. And my friend Paul Anderson wrote a wonderful book called Tau Zero about what happens if you get into a runaway situation and you can't switch it off, and you just get going so fast you're really relativistic. I recommend everybody read that book because it's really one of the great science fiction novels. That's Tau Zero by Paul Anderson, written some 40 years ago.
Yeah, and at the end of the book, as I recall, the starship winds up trillions of years into the future, in one person's lifetime, of course, because of relativistic effects, and they actually go to doomsday. They go to the end of the universe, when the universe goes through a big crunch, and then they witness the next big bang. They witness the creation of a baby universe. Well, let me ask you another question. Dr. Robert Zubrin, who we've actually had several times on Science Fantastic, also critiqued the ramjet engine. He thought there would be drag, too much drag on the Starship, and the Starship, therefore, could never attain light-like velocities. What are your thoughts about how fast you can go on a ramjet engine? Are there problems with drag?
There are. Bob's right about that. There are other constraints, such as the strength of materials, and how much magnetic field you can generate. And so it's problematical, but the Bussard ramjet could credibly get to velocities that are a fraction of the speed of light, perhaps half the speed of light, which is pretty adequate for getting around the local part of the galaxy.
Okay, now let's go to the big one. Every Star Trek fan wants to talk about warp drive, and we've actually had discussions about warp drive on Science Fantastic with other physicists. But first of all, what are your thoughts? You think that one day, far in the future, we may have energies comparable to that of a black hole, by which we could either create an Alcubierre drive, who I've interviewed, or perhaps one day create a hole in space called a wormhole. What are your thoughts? Because that was the basis of the movie Interstellar.
That's really the furthest out we can imagine at the present. It requires a civilization which would have energy densities which are far greater than those that exist in the stars and far greater than we can imagine doing. It also requires some physics to work out right, that the wormhole can be held open and you can get through it. There's an awful lot of things have to happen right. And frankly, I think that's beyond our horizon. That is, we're not anywhere near being a civilization advanced enough to seriously contemplate that. So Star Trek may happen in the 23rd century, but I don't think we're going to get there that soon.
Okay, well, when I interviewed Miguel Alcubierre about his drive, he envisions having a warp bubble, that is a bubble. Inside the bubble, you can zap faster than the speed of light. But he said, he was quite honest, but he said there's a problem. And that is, first, you need fantastic amounts of positive energy to create the warp bubble, and then enormous amounts of negative energy to stabilize it so it doesn't crush you. So he kind of lost interest in it, quite frankly. So what are your thoughts? When you talk to people, do they take it seriously or do they roll their eyes in the heavens and say it's all science fiction? How seriously do you think people are taking the idea of a warp engine?
Some people take it seriously. They are in a distinct minority. It is a bit of an eye-rolling circumstance with positive and negative energies because we don't really know how to produce and manipulate such energies. Let's put it this way. For most people, think of it as quantum physics. Not quantum physics, but it's the physics of what you want to have be true because they want to believe you can quickly get to the stars in a manner that is essentially like surfing space-time.
Okay. Well, unfortunately, we have run out of time for this interview. Once again, our special guest today has been Dr. James Benford. He and his twin brother have written a delightful anthology called Starship Century. You are listening to Science Fantastic with Professor Michio Kaku.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, it's open mic. We're going to throw the lines open because this hour is your hour. Okay, well, let's take the first listener phone call.
Hey, Professor. My name is Jeremy from Battleground, Washington. I listen to you on trn1.com, and I've been reading lately some books by Robert Schoch and Graham Hancock about the theory that civilization may be a lot older than we before thought. And I was wondering, with the find of Göbekli Tepe in Turkey, if you have any comment on that or how you feel about that.
Well, yes and no. It turns out that every year archaeologists discover more and more about the ancient civilizations of the past, and we realize that a lot of our time frames have to be readjusted to compensate for that. For example, many of the things mentioned in the Bible, things mentioned in German mythology, like, for example, the Trojan Wars and the city of Troy, turned out to be true. We actually found the city of Troy. And, however, you can't put some boundaries on this, and that is the Ice Age. The Ice Age ended roughly 10,000 years ago. And before then, it was quite difficult to have what is called modern civilization. We were basically nomads. We were chasing after the deer and the buffalo, and if the deer and the buffalo left you behind, you starved to death. So you had to chase after the deer. You were migrants. You were permanently on the road because your food was also on the road as well. Therefore, cities as we know them were not possible. There were isolated settlements, of course, but you had to have a source of food. Then, after the Ice Age ended, then the age of agriculture started, and then you could have the first stationary villages. Even if the buffalo and even if the deer left, you didn't starve to death because you could plant apple seeds and harvest them in your own backyard. And with the discovery of agriculture came the first villages, then the first cities, then the first empires began to rise out of the desert and the jungle. So when we look at ancient civilizations, recorded history goes back roughly 5,000 years. Beyond that, things get very, very fuzzy. But, yeah, many of the things mentioned in the Bible, you can begin the process of dating some of these things, and you realize that, yes, you can date history going back, recorded history going back 5,000 years. Now, beyond that, things start to get very fuzzy because, of course, writing was not invented back in those days. And so is it possible that there could have been new civilizations between, let's say, 5,000 to 10,000 years ago that haven't yet been discovered? And the answer is, well, yes. Because as long as there was a food supply for these people, like agriculture, it meant you could have stationary cities without having to chase after the deer and the buffalo like a bunch of nomads. But beyond 10,000 years, well, North America was under a half a mile of ice. And so it was quite difficult to create a sustaining civilization when your food basically left, and if they left without you, you starved to death. Okay, well, let's move right along to the next listener phone call.
Hi, Dr. Kaku. This is Carlos. I'm listening in L.A. on TalkRadioNetwork.com. I wanted to ask, I was watching this old TV show called Revolution, and the basic premise is the planet loses the ability to create electricity. So I wanted to see if that was even possible. Seems a little far-fetched to me, but what do you think? Thanks.
Well, you mentioned something very important. We take electricity for granted, but if you look at history going back, we've had three great revolutions in science. The first was the steam engine, and the steam engine made possible the Industrial Revolution and factories and created the modern industrial working class. The second great revolution was the electric revolution that you mentioned. They gave us radio, television, automobiles. It gave us many of the wonders of the modern electric age. Then the third great revolution is the high-tech revolution with lasers and computers. A fourth wave is also coming. The fourth wave is artificial intelligence, biotechnology, and especially nanotechnology. Now, you mentioned what happens if, one of these revolutions is stymied or caught right in the middle. Well, the electric revolution depends upon our ability to harness the power of electrons, and there are ways in which you can conceive of where electricity may not be possible. For example, if the air becomes very humid, electricity does not work well under certain different atmospheric conditions. So yes, it is possible you can conceive of certain scenarios where electricity is not possible. But then some of these scenarios are so severe that people would not be possible as well. So the premise of the TV show is that somehow you could simply turn off electricity and still keep humans breathing and operating normally in our atmosphere. Now, this, of course, affects perhaps life in outer space. Some scientists think that if life in outer space existed, well, they must be able to harness electricity and computers to build rocket ships. But that means their atmosphere has to be similar to our atmosphere, which can sustain lightning bolts without short-circuiting things. For example, if you have a water world out there that is an aquatic species, you might be able to have intelligence up to a point. So if you have fish-like or octopus-like creatures in outer space, yes, they would be able to invent machines. But then when it comes to, for example, the steam engine, they would have a problem because a steam engine requires oxidation. It requires fire. And in an aquatic world, you cannot light a match. Then electricity would be short-circuited because electricity goes right through water. And so those are two revolutions which may not exist in a water world in outer space. So we are fortunate enough to be on a planet where it is possible to have fire, that is oxidation. It is possible to have an industrial revolution and the electric revolution because our atmosphere will support electricity without short-circuiting them. So to answer your question, well, yes, it is possible to create a world without electricity, but that world probably wouldn't have humans either. So to have humans, like in a Hollywood movie, and have no electricity is quite difficult. But yes, we scientists have looked at that because in outer space there could be civilizations that do not have electricity, and their progress would be stunted as a consequence. Okay, moving right along, let's take the next listener phone call.
Hi, my name's Ryan from Spokane. My question is, how many people would go to the Mars base once it's constructed?
Well, you ask a very practical question that billionaires are asking now, specifically Elon Musk, the billionaire behind Tesla, PayPal, and SpaceX, and also Jeff Bezos, the brains behind Amazon and Blue Origins. Well, first of all, yes, people are taking volunteers for real. Elon Musk, pioneer of SpaceX, will launch the first unmanned probe to the moon in many a decade, starting later this year, if all goes well. And next year, he wants to send 2 volunteers circling around the moon in the first manned mission to the moon in 40 years. The cost? Well, yes, you can be one of these 2 volunteers to go around the moon for a paltry sum of $80 million. So if you are a fellow billionaire, yes, you too can join Elon Musk and explore the universe. $80 million to be one of the first people to go back to the moon. Then what about Mars? Well, you have to be careful now because there are some, shady, bogus operations that claim that one day they'll create the first settlements on Mars in a few years. There's a program called Mars One, and it has enlisted many volunteers to be part of the first mission to Mars. There's a problem, a big problem, and that is money. It has no major benefactors. So if you sign up for Mars One, you're not going to go to Mars anytime soon, and that's my personal opinion. But yes, already they have many people volunteering for a one-way mission to Mars. Now, personally, I think we should offer a 2-way mission to Mars so they can come back and talk about it. And that, again, is where Elon Musk comes in. 2024, that is the time when we may have the first manned mission to Mars. And yes, probably you can buy a seat on that. Just go to SpaceX's website, and perhaps there's a place where you can begin the process of signing up. However, I should also point out some of the politics involved. President Donald Trump has now weighed in because of the fact that if we have the first manned mission back to the moon by 2020, let's say, that would be quite a feather in the cap of President Donald Trump. So Donald Trump has actually asked NASA for an accelerated time frame. NASA's time frame is much slower than Elon Musk's time frame. NASA has the SLS booster rocket and Orion space module. Their first unmanned mission to the moon would be around 2020, and perhaps a manned mission to the moon sometime in the 2030s. Well, President Donald Trump has asked NASA, can you accelerate that so that by the end of President Trump's first term, that is 2020, we would have a manned mission that goes around the moon, and then 2024, at the end of a hypothetical second Trump term, there would be the first manned mission all the way to Mars. So to answer the question, right now we do not have an official list of volunteers to go on SpaceX's mission to Mars by 2024. But hey, go to the website and maybe one day we'll see a column whereby you can sign up. But watch out for, well, shady operations that promise you a seat on Mars, but in reality, I don't think they're the way to go. Right now, we have 3 serious proposals to go into outer space. One, of course, is NASA with the SLS booster rocket. Some people criticize their time frame for being too slow. That's why the president has asked for an accelerated program. Then we have Elon Musk with the Falcon Heavy booster rocket. And they've already made history by reducing the cost of space travel rather dramatically. And then we have Jeff Bezos of Amazon. He wants to create a moon base first, perhaps a colony of astronauts that will be part of a permanent presence on the moon, and after that, on to Mars. In other words, we may have a traffic jam around Mars. Who knows for sure? But we have not 1, not 2, but 3 proposals to go to Mars. Okay, well, let's move right along and take the next listener phone call.
Hi, Professor. This is Josh. What do you think about the double slit experiment?
Wow. Well, you are asking one of the big questions in all of physics and philosophy, and that is the reasoning behind the double slit experiment. Well, let me explain. If I have a sheet of paper and punch a hole in it, and then shoot a bunch of electrons at that hole, and then you ask yourself what comes out the other end, most people would say, well, the answer is obvious. You'd have a steady stream of particles called electrons that come out the other end, because electrons are made out of particles, right? Well, that's a naive answer. When you actually do the experiment with 1 or 2 holes, it turns out that at the other end, you do not get an image of just 1 hole or 2 holes. What you do is you get a wave-like pattern, an interference pattern. In other words, the electron has wave-like properties, and it's not simply a dot. It's not simply a particle. Somehow it also has wave-like properties. Now, the double-slit experiment is bizarre, because in order to have an interference pattern from 2 slits, you have to have waves from 2 slits interfere with each other. 2 waves from the top hole and the bottom hole interfering with each other. Now, here is the killer. Shoot 1 electron, not 2, 1 electron at 2 holes, and look at what you see at the other end. If you do this repeatedly, you get a pattern of dots on the other side. And the pattern of dots, once you shoot millions of particles through the double holes, what do you get? You get a wave-like pattern as if the electron went through both holes. Now, at this point, your brain starts to explode, because I said that the electron is a particle, and it goes through 2 holes, leaving a pattern that is a pattern of a wave that went through 2 holes. In other words, the electron is 2 places at the same time. How can that be? Your brain goes berserk thinking about this, and after the break, I'll answer the question. How can 1 electron go through 2 holes simultaneously? How can you be 2 places at the same time? This is not an academic question, because our computer revolution and laser revolution depends upon this answer. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science. And we had a call that came in just before the break, and that is explain the double slit experiment. Well, the double slit experiment simply says that 1 electron, that is a particle, can go through 2 holes simultaneously, creating an interference pattern on the other side, as if the electron were a wave. Now, at this point, your brain starts to explode, because this means that a particle is not really a dot, like Einstein thought, that a particle can go through two holes at the same time. In other words, there is uncertainty with regards to the position of the electron. And this goes to the uncertainty principle, which is the foundation of all of modern electronics. Why do laser beams exist? Why do transistors exist? Why can you hear the sound of my voice going through the ether? It's because of relativity and the quantum theory. So how do we resolve this question? Well, one theory, which is rather unorthodox, but is gradually being accepted by most Nobel Prize winners, that is, my friends, they say that the universe splits in half. This is called the many worlds theory. The universe splits in half, such that in one universe, the electron went through one hole. In another universe, the electron went through another hole, because, of course, one electron cannot go through two holes simultaneously. That's one way to resolve the question. This means that perhaps the universe has parallel universes. Perhaps there's an infinite number of these parallel universes splitting off from each other each time an electron has to go through a hole, or each time a measurement is made. Now, Einstein, of course, hated this idea, but hey, what can I say? Einstein was wrong on the question of quantum mechanics. Quantum mechanics is at the foundation of all of modern electronics, all of lasers, all the wonders of modern technology. Why are they so wondrous? They violate common sense. Isaac Newton would go crazy looking at transistors and lasers, because Isaac Newton would say that the electron is a point particle. Period. End of story. Move on. No, the electron is not just a point particle. This point particle can split universes. This is called the many worlds theory, and it is the leading theory in quantum mechanics today. Now, just to be fair, there are other theories. The Copenhagen interpretation, you can go to any modern library and have your brains blown out trying to read all the literature on this. But hey, what can I say? We physicists have to confront the fact that the electron, in some sense, can be two places at the same time. And the way to resolve it is if the universe itself splits in half. Okay, well, let's move right along to the next listener phone call.
Hi, this is Mike McGee from Duluth, Minnesota. And my question is, how have human beings affected the 100,000-year ice age cycles? And has global warming actually postponed the next inevitable glacial maximum? Thank you.
Well, you ask a very hot question. First of all, what is the ice age cycle? Ice ages do not occur regularly, like on time. However, ice ages are separated by hundreds of thousands to millions of years. And we think it corresponds to the slight wobbling of the Earth's axis. A very slight wobbling of the Earth's axis can build up over hundreds of thousands of years to change the temperature on the planet Earth. And then the question is, what is the link between that and the next ice age? Yes, ice ages do come roughly, periodically, every few 100,000 to a few million years. Right now we are between ice ages. 10,000 years ago, we were under a half a mile of ice in North America. In another 10 to 20,000 years, we'll have a repeat of that. So right now we're in what is called an interglacial period. Now, what does that have to do with global warming? Well, not much, because, of course, we're talking about the Earth itself with cycle times of hundreds of thousands of years. Now, if you take a look at the fact that the Earth has been heating up since the end of the last ice age, yes, the Earth has been warming up slowly and gradually. However, within the last 50 to 100 years, there's been a dramatic spike, a dramatic increase in carbon dioxide, and also with regards to the temperature of the Earth. Now, the fact that the Earth is warming up and it has accelerated is not disputed by hardly anyone, because we see that in the satellite data. We see that in all the ways that we can measure temperature on the planet Earth. Where people would differ is where this comes from. Now, again, can this delay the coming of the ice age? No. We're talking about a small spike. we're talking about, when you talk about ice ages, cycles going back tens of thousands to hundreds of thousands of years. So the warming of the Earth, as far as we can tell, will not affect the coming of the next ice age in 10,000 to 20,000 years from now. However, I should point out that with 95% confidence, most scientists looking at their computer programs would say that the recent spike in temperature is not part of the global warming cycle, that is man-made. But that statement is a statement with only 95% confidence. Okay, well, let's move right along to the next listener phone call.
My name's Ricardo. I'm calling from Detroit. What's the point in going to Mars if a long time ago wiped out all living things? I don't get what the big rush to go to Mars would be. Thank you.
Well, you ask a very important question, because right now NASA is planning to go to Mars sometime after 2030. And as I mentioned, Elon Musk of SpaceX wants to do that even quicker by 2024. What's the rush? Well, to be very honest, there's no reason for a rush at all. We had the rush during the 60s to go to the moon because, of course, there was superpower rivalry between the old Soviet Union and the U.S. of A. And we spent roughly 5% of our gross domestic output on the moon program. Now, think about that for a moment. 5% of the entire industrial activity of the United States of America went into the space program. Then, of course, once we went to the moon and came back, we lost interest, and then it fell down below 1%. NASA's budget today is roughly less than 1%, which is probably normal for a science budget of NASA. What's the rush today? Well, if you think about it, the rush is between billionaires and NASA, Elon Musk of SpaceX and Tesla Motors, Jeff Bezos of Amazon, and of course NASA and Boeing Aircraft. Boeing is the creator of their SLS booster rocket for NASA. Now, I once interviewed Carl Sagan, the late Carl Sagan. I asked him that question. What's the rush going into outer space? And he said, well, there's no rush per se, but in the long term, we have to do it. Because in the long term, life on Earth will be extinguished. Either we'll have giant meteor impacts, like what knocked out the dinosaurs, gigantic volcanic explosions and eruptions, or another ice age, or perhaps the ending of the Earth itself as the Earth goes back into the sun 5 billion years from now. So Carl Sagan said, let's be a two-planet, a multi-planet species, because it's an insurance policy. Not that there's a race to go to Mars, but it's an insurance policy, because one day we may have no choice. Let's move right along to the next listener phone call.
This is Big Al from Chattanooga, Tennessee. And my question is, what's actually happening physically that causes a black hole to have actual gravitational pull? Thank you.
Well, you ask a question that has bedeviled scientists going even before Isaac Newton. What creates gravity and gravitational attraction? Well, Newton didn't know. He just postulated the fact that objects attract other objects by a gravitational pull. Okay? He had no idea as to why, because usually objects move because they're pushed, not because they're pulled. Well, along comes Einstein, who says, I know the answer. Gravity doesn't pull, space pushes. And that summarizes Einstein's theory in one phrase. You see, why are you sitting in your chair today? You're sitting in your chair not because gravity is pulling you to the ground. It's because the Earth warps the space around you, and the warped space pushes you into the chair. That's why you're sitting in your chair right now. Gravity does not pull because there is no such thing as gravitational pull. It's an optical illusion. Einstein says that the Earth warps the space around you and pushes you down. And then you can ask yet another question, and why is that? Like a black hole. A black hole would have objects being attracted to it. Why is it? Well, at that point, Einstein's equations don't tell us. Einstein simply says that if you have mass, if you have energy, if you have a black hole, then it will create a warping according to his equations. Why? We don't know. Okay, it's just the way it is. It's postulated in Einstein's equations. But once you postulate that, it works fine. It satisfies all the data. That's why we give Nobel Prizes now to people who can verify Einstein's predictions about black holes. But why does gravity create this pull? Well, we don't know. It's just postulated by Einstein's theory. And once you postulate Einstein's theory, you can mathematically calculate with very great accuracy the motion of particles as they enter a black hole. Okay, well, let's move right along to the next listener phone call.
Hi, my name is Ron, and I'm calling from Gardner, Massachusetts. I'm listening to WGAW 1340 AM radio. My question is about Martian gravity. I read some material about the International Space Station and how there's bone loss and other bad effects of low gravity. Well, is Martian gravity high enough? I think it's about 1/3 Earth gravity. Is it high enough to prevent that bone loss and other deleterious effects of zero gravity? Thank you.
Well, the short answer is no. First of all, you're absolutely right. Astronauts in weightlessness on the space station basically lose calcium, phosphorus, many vital elements of the muscles and the bone. In fact, Commander Polyakov, the Russian astronaut who set the world's record for being in outer space for over a year, when he came back down to the planet Earth, there's a motion picture of him getting out of his space capsule. He crawled like a worm. He crawled like a worm. There was so much atrophy in his muscles and bone that he could not even come out of his own space capsule and walk. So our astronauts suffer bone loss, some of it permanent, by the way. I repeat, some of it is permanent bone loss. So we have to have our astronauts exercise all the time. We have treadmills in outer space with a rubber band so that you have tension on that treadmill. And you have to exercise several hours of the day because you will have bone loss. Now, as you correctly pointed out, Mars has a weaker gravity than the Earth, roughly 40% the gravitational pull of the planet Earth. They will suffer bone loss, not as much as out on the space station where there is no gravitational pull at all. However, yes, there will be bone loss even on Mars, because of the fact that Mars has a lower gravity. In other words, our body is fine-tuned to live on the Earth. If the Earth's gravity were a little bit stronger or a little bit weaker, our architecture of our body would not be adequate to live in that environment and flourish. That's why we have to do things like exercise. That's why we have to do things like, well, eventually maybe even genetic engineering, so that we can survive on planets with different gravitational pull. One solution to the problem is to spin our spacecraft like a ball on a string. That's very expensive, but yeah, you could create artificial gravity and, quote, unquote, solve the problem of weightlessness, but it would add a tremendous cost to our space program. Okay, well, let's move right along to the next listener phone call.
Yeah, my question is about dark energy. If dark energy, as we know, is the continual expansion and acceleration of the expansion of the universe, how do we know it's this mysterious energy and not the gravitational attraction from some huge amount of mass beyond our range of detection outside of the known universe, and in reality, that instead of everything expanding, that everything within our known universe is actually falling and accelerating towards this unknown mass that's beyond our detection, and it's really just gravity causing that? Thank you.
Well, you ask an interesting question. Einstein tells us that the universe is expanding, and expanding very uniformly, by the way. But then you ask another question. Maybe it's an optical illusion. Maybe it's not expanding at all, but going toward an attractor. Well, that would be non-uniform. Now, it turns out there is a great attractor. It turns out our galaxy is moving toward an object asymmetrically called a great attractor. But that's not the universe itself. The universe itself is uniformly expanding, as we see in the microwave background radiation. That's why we don't believe that the attractor can have enough uniform force to make the universe appear to expand. So in other words, the universe is expanding. Okay, well, that's it for Science Fantastic. Once again, you've been listening to Science Fantastic with Professor Michio Kaku.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Well, in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, let's move right on to the next listener phone call.
The name is William, calling from Bountiful, Utah, and would like to know how the atomic energy plants get started up after they get charged with nuclear energy so that they can operate. What actually starts them up and keeps them going? That's my question. Thank you.
Okay, well, there's a simple answer. The core of a nuclear power plant consists of rods, two kinds of rods. One are the fuel rods containing the uranium. That's what heats up the core and creates boiling water, which creates electricity. But there's a second set of rods which absorb the neutrons, therefore quenching the chain reaction, stopping the reactor. The second set of rods is made out of cadmium, zirconium, and boron. These rods absorb neutrons, so they stop the reaction. So how do you stop a nuclear power plant? How do you start a nuclear power plant? To start it, you insert the fuel rod. Fuel rods are there. You remove the control rods. By removing the second set of rods, the neutron count rapidly rises, and you've now turned on the nuclear power plant. To shut it off, you reinsert the control rods, thereby absorbing neutrons, and the chain reaction stops. Now, the name for inserting the control rods to stopping the chain reaction is called scramming. Now, when you hear about scramming the reactor, that means you turn off the reactor. Where did that word come from? It comes from World War II in Chicago, when Enrico Fermi was creating the first nuclear reactor. He had graduate students. Graduate students sit on top of the fuel rods with buckets of borated water. If it looked as if the reactor was about to explode or get out of control, he would tell the grad students, "Scram." At that point, the grad students would dump the boron and get the hell out. Well, that word stuck. So when you want to turn on a nuclear power plant, you turn off a nuclear power plant, When you want to turn it off, you scram it. And that plunges control rods into the core, quenching the chain reaction. To start it up, you do the opposite. You unscram it, you remove the control rods, and the neutron count rises, and the chain reaction starts up all over again. So that's where we start and stop a nuclear chain reaction. Okay, well, moving right along, let's take the next listener phone call.
Dave, Seattle. I wanted to ask a question. How do you know that the universe is shaped like a bubble when we're talking about such large distances that what we actually see in the night sky is billions of years old, because the light, is that old, and we don't actually see the universe as it existed billions of years ago. So how do we know what the shape of the universe is?
Well, first of all, we're not really sure what the shape of the universe is, but let me tell you how we know what we have. First of all, it was Edwin Hubble back in around the 1930s or so who turned one of the biggest telescopes on the Earth toward the heavens, and he measured their color. When yellow light moves away from you, it turns reddish because light waves expand when they move away from you. When the light waves move toward you, the light beams are compressed like an accordion, and then they turn bluish. So when he turned the telescope to the heavens, what did he find? He found a red shift, not a blue shift. The redder the shift, the faster it goes. So therefore he knew that the universe was expanding. Well, let's take a short commercial break, and after the break, we'll say a few things about the shape of the universe. So, how do we know that the universe is a bubble of some sort? Well, we're not sure because, of course, we're talking about the universe itself. But here's what we do know. We do know that no matter where you point a telescope in the heavens, on average, you get a red shift. Yellow light is slightly reddish. This means that all the stars are moving away from us. Now, at first, you may say to yourself, well, does that mean that the Earth is at the center of the universe? No. It means that the universe is expanding. And the simplest way to visualize that is to assume that the universe is a sphere. Is it really a sphere? We're not sure. But if the universe is a sphere, and you put dots on the surface of the sphere corresponding to the galaxies, and then you blow up the balloon, all the galaxies move away from you. In fact, the closer they are to you, the slower they move. The farther they are away, the faster they move. That's called Hubble's law. When we actually make the measurements, we find, bingo, Hubble's law is correct. Therefore, the simplest way to visualize it is a sphere. However, other people have said that, well, what about negative curvature? Maybe it's really shaped like a trumpet. Or, for that matter, shaped like a saddle on a horse. They would have negative curvature. So, who is right? Well, the answer is we're not sure who is right because, of course, we're talking about the universe itself. But at the present time, it does seem as if the universe is open. That is, it seems to be infinite for all we can measure, but again, we're not sure. So we use models. The model of the bubble is the simplest to use, so we use it. But hey, we're not positive that the universe is a bubble. Okay, let's move right along to the next listener phone call.
Cornell, we're here in Massachusetts. My question, what exactly is hyperspace?
Well, that's a hot topic today. To find out more about it, get a copy of my book, Hyperspace. It was also a bestseller when it first came out. Well, to be very simple, hyperspace simply means a space of higher dimensions, dimensions beyond 3. We know that there are 3 dimensions to space. In order to describe the size of a book or the location of a building, you have to have at least 3 numbers: length, width, and height. But think about it for a moment. Why 3? There's nothing magical about 3 at all. In mathematics, there are other numbers that are much more magical, but 3 is not one of them. So why should the universe 3-dimensional? Why should it be 3-dimensional? Well, we have the ability to visualize perhaps a 4th dimension or a 5th dimension using mathematics. Now, using common sense, you cannot visualize the 4th dimension. Our brain evolved in 3 dimensions, where saber-toothed tigers lunged at us in 3 dimensions, so we're very good at that. We can manipulate objects in 3 dimensions. We're awful at 4 dimensions, and yet your computer, your PC, manipulates 4-dimensional objects all the time. And so it is possible to visualize the 4th dimension. We cannot do it. Now, I work in 11 dimensional hyperspace, the space of vibrating strings. But when I work in 11-dimensional hyperspace, it's all equations. I don't have to visualize it because the equations track it for me. Now, what would it be like to live in hyperspace? Well, let's say on a tabletop you have people that look like a cookie man living on a table which is flat. This is called flatland. You are in 3 dimensions looking down on Flatlander. You have superpowers compared to the Flatlander. You can, for example, stick your finger anywhere in that world and grab things, so things would literally disappear from Flatland. Or you could put things back down on Flatland like a coin. It would simply all of a sudden appear out of magic. Or you could perform surgery on the inside of a Flatlander without cutting the skin. You can reach inside a closed object and pull out the guts if you want and perform surgery. That's the power of a higher dimension looking down on the second dimension. Now, when I was a kid, I used to go to the Japanese tea garden in San Francisco and look at the carp. I used to spend hours looking at the fish, wondering what would it be like to be a fish. Now, think about it. If you're a fish, your eyes point to the side. You can only see in two dimensions, forward, backwards, and that's about it. You live in a two-dimensional world. And then I imagine that a three-dimensional person, i.e. me, could reach down and grab a two-dimensional fish. What would the fish see? The fish would first of all see strange beings that could move without fins, beings that breathe without water, magical beings that could perform surgery without cutting their skin. Think about this. And I put the fish back into the pond, what a tale the fish would have to say. At the turn of the century, many people were fascinated by this idea that there could be beings living in hyperspace. And that's where the idea of ghosts comes in, because some people think that maybe ghosts live in the fourth dimension. And theologians used to write about that. Theologians at the turn of the last century would actually write monographs saying that when people die, maybe their souls go to hyperspace. Well, today we don't know whether hyperspace exists or not. The theory that I work on, string theory, exists in 11-dimensional hyperspace, but that doesn't prove it. So we can visualize it mathematically, but proving its existence has not yet been done. However, at the Large Hadron Collider outside Geneva, Switzerland, the machine got the Nobel Prize for several physicists for working on the Higgs boson. But not only that, we hope to find sparticles. Sparticles are super particles. Particles predicted by string theory. They represent a higher octave of vibrating strings, but we've never seen one. But we think that's what makes up dark matter. Dark matter is invisible, fills up most of the universe, much more plentiful than ordinary matter, and sparticles could be dark matter. So in other words, the next vibration of the string could explain dark matter. We are the lowest vibration of the string, things we can touch, but there are other dimensions out there. So in other words, the question of hyperspace is no longer academic. Most of the universe may live in hyperspace. Okay, well, let's move right along and take the next listener phone call.
My name is Elizabeth, and I'm calling from Boulder City, Nevada. Bees, why they make hexagons to store the honey in? Why the six-sided shape? Is that the most efficient shape?
Well, yes, it could be the most efficient shape. Realize that if I blow soap bubbles, what determines the shape of a soap bubble? Believe it or not, it is a shape with the minimum area. So, when you get all sorts of crazy configurations of soap bubbles, why? It's because it's the configuration of minimum area. And same thing with the hexagon. It's one of the shapes that allow you to maximize the amount of honey produced with the minimum amount of wax. Pretty good for evolution, I think. Okay, well, let's take another short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. The lines are open. Give us a call, and maybe you can get on Science Fantastic. Okay, well, let's move right along now and take the next listener phone call.
My name is Michael. We are in Mobile, Alabama. What is the name of the core of the planet Earth? We know that the equator is considered the center. We want to know if there's a geographical name for the core of the Earth. Thank you.
Well, there's no formal name for the core. However, the core has many shells, and each shell has a name attached to it. But there's no one name for the core of the Earth. And then you may ask yourself a simple question. Well, how do you know? No one's ever been down there. How do you know what the center of the Earth looks like? The way that we scientists do this is by listening to earthquakes. Every time there's an earthquake, we have sensors all over the globe. An earthquake starts at one point just beneath the surface and creates a shock wave. That shock wave goes through the center of the Earth and slows down and speeds up, depending upon what kind of dirt that it went through. If it went through dirt of higher density, then at that point, we probably have the most distortion. Anyway, but looking at echoes that are created by the original shock wave going through all these layers, we can then reconstruct a map of the inside of the Earth. It's not perfect, of course. In fact, I've seen pictures of it. The center of the Earth looks more like an onion, a large blob with things coming out like dendrites or tentacles coming out of the core. So that's what the core looks like. And we think that that in turn is partially responsible for the earthquakes that we get. But as far as the name is concerned, we don't have names other than the scientific names for the various layers inside the core. Okay, well, let's take the next listener phone call.
Hi, I wanted to know, is there an infinite space? Does it keep going, or does it have a drop-off? Just stops. Thank you.
Well, you ask a question for which we physicists are not quite certain. Right now, most physicists are leaning toward the idea that the universe is infinite. But if it's infinite, where did it come from? It had to come from a point, right? Well, realize that this is a very hot topic, at least it was 400 years ago. About 400 years ago, there was a former Jesuit priest who was burned alive in the streets of Rome for simply saying that there could be aliens, there could be other star systems out there, just like our own star system. Well, the Catholic Church was not happy at all. Not happy at all. Because here was this renegade priest, a vagabond priest that would go from capital to capital, claiming that there could be other stars out there with different kinds of planets. And then he said the universe is infinite. He was perhaps the first person ever to entertain the fact that the universe could be infinite. Why is that dangerous to the church? Because an infinite universe has no center. Therefore, our universe, our Earth, and our Bible cannot be the center because the universe has no center. Is the universe really infinite? Well, some people say it cannot be infinite because if it were infinite, sooner or later you would perhaps find an end someplace, and then you have to ask yourself a question, what is beyond the end of the universe? The mind goes spinning thinking about an universe of infinite length. Well, which is it? Is our universe infinite or closed? The short answer is we don't know. The data is not yet precise enough to answer that question. However, most scientists would lean toward the idea that the universe is open. It would open toward another death in the universe. First, we had the Big Bang. Then the universe is accelerating. Then we thought it was slowing down. We thought it might even reverse itself and contract. Nope. The universe is speeding up. It's accelerating. This caught everyone by surprise. Because we thought that sooner or later you would reach rock bottom. Nope. There's another layer beneath the quarks. Now, let me explain. On a large scale, we have galaxies. Below that, we have stars. Below that, we have planets. Below that, we have animals like you and me. So we have a hierarchy from the very top all the way down to the very bottom. But if people like Bruno had their way, perhaps the universe has no center at all. That was a horrible idea for the Catholic Church because the Church said that the earth is the center of everything. And if not the earth, well, at least the sun. The sun would be the center of the universe. And here comes Bruno who says, no, there's no center at all. The universe could be infinite. Okay, well, let's move right along to take the next listener phone call.
My name is Rudy. I'm calling from Eureka, California. If our moon now controls the tides and, that's up to the oceans, how was it back then before the moon was the moon? What was going on Earth with tides?
Well, you ask a very interesting question. If you actually look at the numbers, it turns out that the Earth is about 4.6 billion years old. You got that? 4.6 billion years. Now, how old is the moon? Because you ask yourself a simple question. What would it be like for the tides without the moon? First of all, without the moon, there's no tides. The tides are caused by a combination of the sun's gravity and the Earth's gravity, but most of it coming from the moon because it is so close. So the tides are thereby closely linked to the moon, but at one point there was no moon, and that is roughly 4.1 billion years ago. The dates, of course, slightly change depending upon how recent your book is, but most people would say that the moon is about 4.1 billion years old. So what was the Earth like back then? Well, realize that the Earth way back then was probably molten. It was cooling down. There were probably asteroid collisions all the time taking place. And as a consequence, it was a very rocky environment. And at that point, there were no tides because the moon hadn't been created yet. 4.1 billion years ago, the moon was created. An object the size of Mars plows into the Earth, blows out the center of the Earth, allowing the center of the Earth to condense into our companion here on the planet Earth. And so we see, therefore, that it is possible to visualize the Earth without a moon. However, we think that these tides are very important because not only do they give us the tides, they also give us the rings of Saturn. They also give us the fact that the Earth once upon a time had a ring. That's right, when the moon was blown out of the Earth, computer programs show that a ring of debris formed around the planet Earth. So rings are caused by tides, we think. We're not certain because no one was there to watch it happen. But yeah, we think that tides actually created the ocean, influence the oceans. So tides are extremely important. Not only that, but the Earth creates tides on the moon. The moon is not exactly round, believe it or not. Moon is actually slightly football shaped. Why? Because the Earth tugs on the moon, and that's why only one side faces the Earth. You've never seen the back side of the moon unless you've seen a photograph from the Russian and American space programs. Fantastic with Professor Michio Kaku. The lines are open. Okay, well, let's move right along and take the next listener phone call.
My name is Steve, and I'm calling from Denver. How far does the gravitation of the Earth reach into the space? And does it have anything to do with the objects fallen, such as, meteors and comets, and smashing into the Earth?
Well, you ask a very interesting question. Where do meteors and comets come from? They come from outer space, but how does the Earth grab them? The Earth has gravity, as you pointed out, and the gravitational tug of the Earth will grab onto meteors and comets, and maybe one of these days, God forbid, it will actually hit the Earth. The question is, how far does gravity extend? And the answer actually is infinite. The gravity of the Earth penetrates deep space. Now, you may say to yourself, well, I saw a movie where that wasn't true. Well, those movies are wrong. The sun holds the solar system together by gravity, and the Earth has gravity also, which holds the moon in orbit. But comets and meteors that get too close to the Earth could be pulled in, striking the Earth as a consequence. So we think, therefore, that the dinosaurs themselves were wiped out as a consequence of such a collision 24 billion to 36 billion years ago. We're not exactly sure precisely what happened, but it just goes to show you that the reach of gravity is infinite. Oh, by the way, some people say, how can that be when there's weightlessness? Doesn't gravity stop in outer space? How come our astronauts can wave at us upside down unless there's no gravity in space? Well, that's wrong. Outer space has plenty of gravity. But even though it has plenty of gravity, weight can go to zero. Now, how's that possible? Because the moon, for example, is in free fall. It doesn't hit the Earth because the Earth is circular, but the moon is actually in free fall going around the planet Earth. Now, therefore, rocket ships are also in free fall, and according to Galileo, everything falls at the same rate. Therefore, in a rocket ship, you are falling at the same rate that the hull of the rocket ship is falling, and that gives you the illusion that you are weightless. You actually have plenty of weight, except that it's all blurred together because your body tells you, though, that no, it has to be weightless. He's floating. No, you can float even in the presence of gravity. So gravity, in some sense, plays tricks on you. It's invisible, but the more the mass you have, the more gravity you have. And even though the Earth has plenty of gravity, you can still be weightless if you fall at the same rate. Now, I do this experiment for my students in astronomy. I get a small marble, and I get a very large ball, and I drop it. But before I drop it, I ask the students which will land first, the big ball or the little ball. Well, almost everyone says the big ball will fall first because it's bigger and races to the ground bigger. Wrong. You can do the experiment in your own living room. It turns out they both hit the ground at the same time. Now, if one hand is your space capsule, the other hand is your spaceship, you notice that both your hands fall at the same rate. Therefore, that's why gravity can play tricks on you. Okay, well, let's move right along to the next listener phone call.
This is William calling from Alabama, and I had a question on consciousness. What is it, and what are the thoughts behind it?
Well, you ask a $64,000 question of which there's no consensus in the scientific community. So I decided to quantify consciousness myself in my book, The Future of the Mind. I claim that animals are conscious. In fact, I say that the unit of consciousness, 1 unit, the smallest unit of consciousness is a feedback loop like in a thermostat. That's right. I say that even a thermostat has a certain form of consciousness. 1 unit. Now take a look at a plant. A plant may have 10 units of consciousness because it has to know where the sun is located. It has to know where gravity is pointed. It has to know about moisture. It has to know about all these things, which requires a little bit amount of intelligence. Therefore, I would say that animals are also conscious because they also have feedback loops. They have 3 kinds of feedback loops. One is the back of the brain. That's the brain of the crocodile, reptilian brain, the brain of passion, territoriality, fighting. That's the back of the brain. The center of the brain is your limbic system, emotions. Emotions are in the center part of your brain. That's the monkey brain because monkeys are very sociable and smarter than rabbits. So the brain grows from the back to the front. Then the question is, what is in the front, and what do we humans look like compared to the animals? Well, we have the prefrontal cortex, and most animals don't have much of a prefrontal cortex. We know what time it is. We know how wet it is. We know what's going to happen in the future, a decade from now. Animals haven't the foggiest clue about the future. So in other words, I claim that it is our understanding not of position, because alligators can do that, not of our social rank, because monkeys can do that, but projecting into the future. Our brain is a simulation machine. It's constantly predicting the future.